I'll just wait for a few minutes for others to join and just recap what we covered last week. Okay, right. So I'll start today's class. So before that, we'll recap what we covered last time. Right. So first of all, we saw about the my class class, right? It has a private section where we just define the data variable of integer data type. After that, we have the public section where we define the constructor, which takes underscore data of data type integer. Okay. And then it sets the underscore data to data. Okay. Second. Yeah, should be good to go. Yeah. So that's the portion of the constructor where it sets the data, and then in sorry, and then inside the body of the constructor we have the statement which says it's constructed. So basically, this is the part which is called when the constructor gets called. Okay. And then we have the display function. Okay. And the main main function. We have the my class data type. Okay. With as in the custom data type. This is the class name object. We pass 7 to it. So the constructor gets called. Okay. And then we have this display object, which is this function. Yes. But if you see inside here, which is this display function is public and friend, which means this display function has access to even private member functions and variables of the class. So yeah, it takes my class object, okay, as a reference, and then um, yeah, it takes my class object as a reference, and with basically that's the input type, and with that it can do some manipulations. So for example, here we complete the body, which is outside the function. We can complete inside here also, but the idea is that when you declare something as a friend, okay, that function, even if it's outside, so like we have this example here, it has access to the internal member variables. That's the idea. So here it takes the A object, okay, and we're able to access the dot data, and we can do the dot data and access the data member variable, which is actually private, okay, and actually print it, right, which was set through the constructor here. All right. After that, we saw about inheritance. Okay, so there are two portions to it. You essentially need two classes to like use this feature called inheritance in C++. So the first one is you have a base class, and let's say it has three sections. The private section, which is the integer data, let's say 1b, the public part, which is the integer data 2b, the protected, which is integer data 3b. Okay, and to define another class which is derived from this base class, this is the syntax. So you define class derived, use the colon, and public, and then base. Okay, so this is the derived class. I do not define anything here, so this will be private. Okay, so integer data 1d, public data 2d. Okay, and then I just defined a function and called various stuff. Okay, so maybe I'll just what? All right. Yeah. So and then this is the public portion of the derived class. After that, we have the protected portion. All right, and then we have the main function. Okay, so have we define two what do you call it? Sorry, yeah, we define two objects. Okay, one is of data type base, another is of data type derived. Okay, so two classes B and D. So these B and D are the objects of that class. Okay, and then I just call various things, very similar to what I do here. So the motivation to write this portion of the code, as we saw last time, and again this portion of the code, is to see which portion you can call where, and what does it even mean to call this. We're not doing anything with the data member, yes, but even have access to that to perform any operation, okay, you need to understand how the um, accessibility in a way works. Okay, so for derived uh, classes, okay, they inherit the base class. So base class itself, okay, if you go through here, so data 1b is private. Okay, remember, okay, maybe I'll put it here also. So yeah, data 1b is private, so you can't access it anywhere outside the class. So that's hence it's commented here. Okay, it will throw an error. Okay, compilation error. Okay, so data 2b is public. That's absolutely okay. You can do b dot data 2b and access that. It's absolutely okay. The third one, b dot data 3b. Okay, that's protected. You cannot access it outside the class. Okay, but protected can be accessed once it is inherited. Okay, so the inherited derived class has access to data 3b. It doesn't have access to data 1b. It has access to 2b. 2b is anyway accessible outside the class also. Okay, so that's the three things to remember. Okay, so that takes care of data 3b. Okay, after that we try to access data 1d from d. Okay, so that is private, so anyway can't be accessed. Data 2d is public. Okay, so that's fine, you can access it. Data 3d, well, data 3d is inherited, right? But it is protected. You can't access data the derived class has access to data 3d 3b. Okay, wait a minute, sorry, yeah, my bad. I meant this data 3d, it has access to the protected member data 3d, but it is not accessible outside the class. Okay, so here we are trying to access it outside the class, so hence not possible. It will throw an error. Okay, data 1b is private again. Okay, so you can't access it outside anywhere. But remember, I'm trying to access the data 1b member, which is derived from base. So as in so when derived classes try to inherit something, okay, they have a copy of whatever the base class has, okay, as their own copy. It'll be a little more clear in this example, okay, when we go through it. But yeah, that's something to keep in mind. And data 2b also is accessible. So you can try to access the data 2b member which got inherited from the base class. Okay, so this data 2b is a member of D and this data 2b is a member of B. Okay, and data 3b is anyway protected, so can't be accessed outside the class. Okay, so now if we go through sorry, this example again. So data 1d, yes, accessible because it's private. So this inside the class, it is accessible. Data 2d, yes, it's inside the class. Even if it's public, it's accessible. 3d, yes, it's protected, but again, inside the class, so not a problem. Data 1b, not possible because it's private to the base class. Okay, here I'm trying to access this the THIS pointer using the THIS pointer. I can access the current classes members itself. Okay, so this explicitly accesses the data 1d, which is a member of the current this class. Okay, so you have this to be okay, so which is accessing the data to be which it inherited, not the data to be which is of the base class. Okay, keep in mind when inheritance happens, so it creates a copy for itself. So we're accessing the data to be which is from the derived which is inherited by the derived class. Okay, data 3b again, it inherits the protected function also, so we can access that. Here I'm trying to access the 2b and 3b, okay, which are the member functions of the base class itself. Okay, so I use the base class as a namespace and then access them. Okay, so 2b is accessible, 3b is also accessible because it's protected. Okay, all right, hope this is clear. Then the other thing we saw is uh, you can have functions, okay, so different names, and let's say it's this is a very simple example. Takes I as input, f and g two functions, and one just prints I, another prints 2i. Okay, we have two uh, classes. So one is the base class b and the derived class we try to derive. It's just empty class, it's not does nothing, but anyway we can do that. After that, if you try to call b dot f6, okay, that is public, so you can call it, no problem. B dot g also you can call it, no problem. But if we see d dot f, how can we call it? Because we can, because derived class inherits the functions of the base class also. So derived class has the definitions for f and g on its own. So for itself also, it has access to them. So once you call them, this also works, as in it doesn't throw error or nothing. It's a very valid code. Okay. After that, okay. So something we were a recap on functional overloading. Okay. So first of all, let's say we have a function called func, which doesn't take any input, and there's some body. Okay. Another, we can define the same function but taking different inputs. Okay. So here it doesn't take an input. Here it takes integer. Here it takes float. Here it takes double. All right. So now, because of the same function name has different portions in the body. Okay. Different code which depends on the input that you're passing. So this is essentially called function overloading. You overload the function with different input data types, and depending on each of them, the body portion, the body section of the function can change. Okay, and then you can call functions like this. So, yeah. So, okay. So similar to that, similar to previous this example, we define the base class again as such with f and g definitions, and then define the derived class from the base which inherits from the base class. Okay, define f, g, and h. Okay, but here one has to be careful because f also gets inherited. Okay, and we have another redefinition of f. Okay, this f gets used for the derived class, so this is called function overriding. Okay, we had g, another g, but different input parameters, so hence it's called function overloading. And anyway, the derived class can have its own functions, extra functions, different from the base class. Okay, that's perfectly allowed. So if we take the base class, okay, and then are there any questions? Oh, okay. Right. So if I have the base class B, right, is basically the we're defining it again. Okay. So derived class has D, fine. We call the function f, which belongs to B. Okay. So f and g here are valid, so it will try to print I and 2i. That's what we expect. If you have D and you call f, okay, it will use the overridden definition, not the definition it inherits. Okay. If you try to call g, depending on the integer or float, it tries to print the different bodies. Okay. And h, it will definitely print this one because it's just an extra function. Okay. All right. With that, we can start this week's topics. Okay. So we'll learn about typecasting. Sorry. I have seen. So the usual, we have the main function and iStream for printing stuff. So first of all, let's define few variables. Okay, let's say this is 7. Float. Let's say 4.5. Double. The variable name is D, which is, let's say 8.9. Okay. Important thing to remember. Okay. Here this is so since I'm on a 64-bit machine, okay, the default behavior for integers is 32 bits. I'm it's a bit more specific. It's a 64-bit machine. Again, I'm on an ARM architecture Mac, but in general, if you're using x86 architecture machines like from Intel or AMD, so this also sort of similar. If you have the 86 64-bit CPUs, usually the integer will take 4 bytes, a float and integers. A double will take 8 bytes, which is equivalent to, this is 32 bits. Sorry. And this thing 32 bits. Okay. And this thing 64 bits. Okay. So let's say I try to just print these numbers. Okay. All right. This will print the I, F, and sorry, my bad, and D. Okay. Let's compile this and see. So prints perfectly 7, 4.5, and 819 as expected. Okay. Right. Now let's set b equals to I. Okay. All right. And again print the same D. Okay. All right. I think you guys can sort of expect what's going to happen, but let's print this and see. Okay, it prints 7. Basically, what we did is we overwrote whatever value D had and filled it with I. So I had 7, okay, and double is uh, a number, okay, which actually stores the real numbers, and I has a integer because that's the data type, okay. So after overwriting, it will have 7, okay, which is an integer. All right. So uh, if you are not familiar with how numbers are represented, just a brief recap. Double and float are used to store real numbers. Okay, so they follow the floating point standard for 32-bit and 64 bits respectively. Okay, and it's the way the standard works. Okay, it's possible that you might not be able to represent integers even exactly. Okay, if you have too big of an integer, you might not be able to even represent that exactly. You'll have errors in the sense there'll be a range of depends on what numbers you are trying to represent. There'll be a range of numbers which will always get rounded off, okay, to the nearest chosen value. Okay. In any case, that's the case for FND. It just so happens that 7 is too small, so you can represent that digit exactly in FND. Okay, just something to keep in mind. And for integers, there is a limit. So if it's 32 bits here, so that will be 2 power 31 plus minus 1. Okay. Uh, if it's unsigned, sorry, if it's signed, if it's unsigned, then you can represent, I think that will be 2 power 31. Yeah, plus 1 or minus something like that. So it will be 0 to around 4 billion, I guess. And if it's signed, then it will be plus minus 2.4 billion or something like that. Okay. So numbers from minus that 2 point some billion to plus 2 point some billion. Okay. Those numbers you can represent exactly, only the integers. Okay. So that's the uh, feature. Okay. What you get with 32-bit integers. Okay. On 64-bit, you get even more. Okay. Much larger numbers, access to much larger numbers. All right. Okay. So that's sort of the small recap. So here, what happens is we do expect that D to have the data of I, which is 7. Okay. But there is a conversion of data type happens from here integer to a double. Okay, so this is called an implicit conversion, or you can say it's a implicit typecasting. Okay, from integer to double. Okay, all right. This is implicit. Yeah. The other way you can do the same thing is write the same code. Okay, but instead put a bracket and put the explicit conversion, the data type of D itself. Okay, and then print the same. Okay, so that also prints 7. Okay, as expected. The difference being that this is called an explicit cast. So it's also typecasting. So what we're seeing here is typecasting is basically you're casting one type from one to the other. Okay. So here a conversion of integer to double happened. And from here also the same thing, but the difference between them is here it happened on its own. All right. Just a second. All right. So here it yeah, another thing is if you guys have any questions, you can interrupt me in between. Okay. Yeah. So here the conversion happened implicitly, as in compiler itself did it. It observed that you want to convert a integer to a double, okay, and then write the value here. So it did that, no problem. So when the compiler itself does some typecasting on its own, so that's the implicit typecasting. And if the developer or the user wants to explicitly make sure that this is happens in this way and something, you can do an explicit typecasting by mentioning the data type. Okay. And so this is again also a typecasting from integer to double. Okay. The another important thing to remember here is this type of typecasting is the C style way of typecasting. Okay. We'll look at the C++ way, but just for now, for understanding, remember you can just put anything in the bracket and then that typecasts explicitly to the data type on the right to the one you're mentioning. Okay. All right. The other thing you can do is define, let's just no need to define, okay, we'll reuse it. This time I'll just comment this. Okay. I'll define I, okay, equals to B. Okay, next. And then print B. Oh, sorry, I. Okay. So remember, I just commented these two. Okay. So now the only code you have is the previous values, and then there is something we have done here. Okay, and then we're printing the value. Okay. Can anybody tell what's going to happen? Just take a guess. What will be the output of the code? Okay, right. Because we are converting a double, okay, which has some decimal parts. So essentially, when we convert it to integer, the decimal portions get chopped off. Okay, that's sort of the essential idea. Okay. Now here, this is also a form of typecasting, and we can see the result print 8. Okay, but and yes, of course, this was done explicitly. Okay, so I'll just mention that. I hope this is clear why this is explicit, because we're explicitly mentioning the integer conversion of data type. Okay, so it's the explicit cast from double to integer. All right. But what if I did not have this? So as in, let's say this is not there, and then just have this, and this is the implicit way of doing it. All right. What do you guys think will happen? Let's run the code and just see. Okay. So here it also does implicit cast. Okay. All right. But ideally, it's how to put it, better to be more clear about what is the conversion that you want to do. Okay. Here it also worked again, right? So just compile and run FSC. It worked. But one has to be careful because you're actually converting from a uh, higher data type in a way, okay, in hierarchy to a lower data type. In the sense, they are both okay, one is definitely 32 bits, another is 64 bits, okay. But when you're trying to convert numbers from, let's say, 8 D or something, so here it's 8.9 to some integer, okay, then implicit cast might be not so obvious always, okay. So in cases like this, it's actually advisable, okay, so to have the explicit cast, all right, so that your intention is clear that you want to convert the data type, okay, to integer and then overwrite it. Because if you remember, the representation of bits in D and I are actually different. D is represented using the floating point standard, okay. The bits in I are, which is integer, are represented using the 2's complement method. Okay. So the way, so definitely there are zeros and ones in D and I both. Okay. And yes, of course, this has 32 bits of them and this has 64 bits, but the same 32 bit or same 64 bit can be looked at differently using two different methods. Okay. So the IEEE 754 standard, which defines the floating point standard, okay, will look at the same 64 or 32 bits differently than what the 2's complement will be. Okay. Remember, the floating point standard is for floating point numbers like the real numbers, and the 2's complement standard is for the integers. Okay. All right. I think that is hope that is clear. Okay. Then yeah, another thing you can do is you can set the precision of your printing the values. So for example, here it prints 8.9, right? Let's say you want to print some number which and usually by default it will only print till certain decimals. Okay, CPP has that default value. If you want to increase the number of decimals you want to print, okay, you can set the precision, okay, using this function called the, I think it's the yeah, standard set precision, not precision, just precision. Okay, pass that to standard cout, and then the number you pass to it will determine how many decimals you want after your decimal point. Okay, definitely there is a point of diminishing return because there's only so many digits that you can represent accurately, be it float or double, both. Okay, brush up on your representation of numbers if you are not familiar with them. But essentially the idea is that because sometimes these decimals can be infinitely you essentially sometimes need infinite precision, right, to represent an actual number. But again, on computers in real life, we have only finite digits. So we have like 32 digits or 64 bits only, right? So only among these bits, it's and using the whatever standard we have, okay, there is a sort of a best effort we do, and only certain decimals after the certain decimals for both float and double are only accurately represented. Others, if you try to represent also, it's like other bits or other digits are essentially garbage. Okay, right. So just to yeah, excuse me. Yeah, just to give you the hierarchy. Okay, so bool comes first, then character, then short int. Okay, then integer, then unsigned integer, then long, then unsigned, then long, okay, then float. Long is when you use want to promote your like use the longer width available in your architecture. So by default, integer is 4 bytes. So when you add long to it, it becomes 64 bits. Okay. Um, long is supposed to be longer than that, but then again, there's a cap on 64-bit system. So longer will also give you the same 64 bits. Okay. Double. Okay. Long double. Again, there's no much difference with double and long double if you are on 64-bit systems. Yeah, that's it. Yeah. And then just final returns. Okay. On that. So I hope no any questions here and doubts. Okay. So let's look at another example. So this is the stream again, as we include that. Define the main function. Have an integer I, which will have let's say 3. Okay. Then we'll define an integer p, but more specifically a pointer, an integer pointer p. Okay, which will keep the address of I. Okay. So sort of one can think that the address of I is now in P. So if you try to dereference P, okay, it accesses the value at I, which is 3. Okay. And then let's define A as some 10 values. Okay. It's just a C style array. Okay. And then let's define uh, data type, the variable D within it, data type double. This we can have like say 10.5. Okay. And then another pointer, okay, to the same D, we'll call it Q, okay, and pass the address of P. Okay, simple. There's another pointer that we'll define, which is the void pointer. Okay, we'll just call it R. We will not set it to anything. Anyway, it's the void pointer. So, yeah, okay. Now let's try to um, set, okay, a pointer Q from P. The set Q, okay, P is pointer here, which is integer type, and set it to Q. Okay. Remember, pointers essentially store the address. Okay, so technically speaking, the size of Q and P are exactly the same. Whatever is the maximum size of my system. So here it will be 64 bits. So the values that Q can store, okay, and P can store are exactly the same. Okay. Remember here we had a different case where we are explicitly casting or whatever basically a typecasting where we lose bits. All right. So in this hierarchy order, if you see, bits actually increase. Okay. When you demote something, you lose information. When you go up the ladder, you don't exactly create more information, but it's like you can represent the same number more accurately in a way. One can think of it. Think of that. Okay. So that's sort of roughly the idea. Okay. But here it's not just a number, it's just the pointers. And Q and P themselves are storing 64-bit unsigned integer. Okay, unsigned long integer, you can think that way. Okay, but what do you guys think will happen when I try to call this line, right? Let's run this and see. It throws an error, okay? Because again, the answer is also in front of you guys. We're trying to convert a double pointer to an integer pointer. Okay. While yes, it is true that the values that Q and P store are both 64 bits, and yes, they're both integers. But a very important point about pointers is that the data it is actually pointing to. Q points to a double. Okay. P points to data which is integer. Okay. One cannot just write the bits like this, okay, implicitly. Here there's an implicit casting we're trying to do, okay, and hence the compiler throws this error because again this is a very like a source of mistake, okay, a blunder, because if it overwrites those same bits, right, but then does it know that you want to convert it to like and like read the same bits which were once uh, represented for 3, okay, so 3 will have a representation, right, in integers 2's complement. Same bits when I try to read after overwriting to Q, I'll try to read that as double. Will they give me 3? Maybe, maybe not. I mean, uh, it depends really. But is that something that we intended to do? Maybe. I mean, that's possible. Maybe we intended that or not. The point is, compiler doesn't want that ambiguity through implicit casting. Okay, so this is not allowed. Okay, so maybe let's throw a error. And now let's not comment here. Let's try the opposite one. What do you guys think will happen? Try to compile. Okay. Again throws the error because the intention is not exactly clear. And when you're trying to convert pointers, okay. Typecasting with normal inbuilt numbers, it's not very difficult, as in it's kind of straightforward. You have one integer, there's a hierarchy to it, okay. You keep converting one from other, there'll be bits chopped off or whatever. That's uh, absolutely okay. But when you have pointers, it needs to be very clear how is the data type going to be handled. Okay, because you're trying to write a different pointer of different data type to another pointer of another data type. Okay, so again, this also throws error. Okay, so implicit casting of pointers is not allowed. Okay, that's essentially the take-home message. What we can do the same for the same thing is, right, you convert Q, okay, to sorry, convert P to Q, okay, but remember Q is what? This is a double pointer, so you have to give a pointer. Okay, so the data type is determined for whatever casting you want to do. Okay, that is determined by the variable data type itself, as in the pointer's data type itself. Okay, so this will be a explicit casting. Implicit is not allowed, so this will be a explicit casting from integer pointer double pointer. Okay. All right. Now, what do you guys think? What will happen? Will this work? Not work? Okay. I can just run it and show you guys. It's absolutely fine. Okay. Compiler throws no error. The reason being, when you are explicitly saying how to convert your pointers, okay, like this. This is the C style method. We'll see other methods in C++ later on, but just understand the concept first. Okay. So when we try to convert the pointer P, which is integer, right? Integer pointer, as you can see from here, you explicitly give the line which says double point. Okay. Which means you're trying to convert an integer pointer to whatever is inside the bracket, which is double pointer. Remember, do not forget the star, okay? You're still converting a pointer to another pointer, all right? Because Q is a pointer here, all right? And Q is happy with it because it itself is a double pointer, okay? And it is getting a converted double pointer. So no problem there. So now the thing is, if you convert it, okay, now it has a new address. Previously, it was pointing to D, which is a double and had 7.5. Okay. Now it has the address of P. Okay. Which is pointing to actually I. Right. So let's print that and just check what is it actually pointing to. Right. Let's just say dereference of U. Okay. Um, U. Then we'll just do it once before. Okay. Setting it and then after. All right. Yeah. So if you see 7.5 is absolutely fine. We had the double 7.5. It was pointing there. So it printed 7.5 when we try to dereference it. Absolutely fine. But when you try to print Q after it gets P, it throws some random number, some garbage. Now, why is that? It is such that it is such, okay, because the number 3 is represented with some bits on like with integer I, okay, and P was pointing to it. So those same bits are now treated, they got copied to Q, okay, through this conversion. But now the same bits which were in one definition, in one representation of 2's complement were represented as 3, okay. But the same number, okay, when represented using the floating point representation gives you this number, okay. Hence the difference. It doesn't print 3, okay? It prints the representation of integer 3 in floating point. Okay, all right. Because 3, sorry, 3, yeah, 3 is represented as 2's complement. Okay, all right. Similarly, what happens, let's say we try the opposite way. Basically, what we did try to do here. We set P as Q as P, okay? But this time explicitly give the data type of P. So P is integer pointer. Okay, so I'll just do that and set Q. Okay. All right. So any guesses? What do you guys think will happen? You guys give a guess also. It's okay. It's okay if it's wrong. All right. Just print that and see. Okay. Yeah, it's a valid method. You can always convert it. All right. Um, the compiler doesn't throw any errors, right? But let's try to print and then see. I could print it before and after. let's do that, but let's also comment so that we have the previous values and no confusion arises because of that. Okay, I have this and then it's comment done. All right. So we try to print P before, which is 3, not a problem. Q is pointing to D here, right? So which is 7.5. So apparently, oh, yeah, that is, yeah, did I make a mistake? No, it's fine. Okay. So Q when converted from D, okay, so there's some representative of 7.5. Apparently, when you try to read it as 2's complement version, okay, you get 0. Right. So one has to be careful while converting pointers, okay, of one data type to another. You should be careful mainly because while yes, it converts, it explicitly casts one pointer to the other. Okay, this explicit casting transfers the bits. Yes, so it's basically like you copying the bits. In essence, you're copying the address. Absolutely yes. But now because the data type also changes, the value which the pointer is pointing to gets changed. Okay, so it's possible that one time it was yeah, so it's possible that one time it was represented using floating point numbers, and the other one it is represented using two's complement for integers. Okay, so the same number, okay, might be represent because of the representation look completely different in the other representation. All right. Okay, so this is explicit casting from double pointer into integer pointer. Okay. Now let's take a look at another example. Remember, we didn't just define Q P from I and Q from D. We also have this R. Okay, this is a void pointer. Let's say I define P, R equals to P, like just like that. Very much similar to these two cases. Okay, but remember we had errors here. What do you guys think will happen here? If I have this line. Okay, just show the answer. Okay, so it doesn't throw an error. Remember, in this example, at 13 and 14 lines, okay, we saw it actually threw an error, but it doesn't for this one. Can anybody try to take a guess? Why is that? I'll give you the hint, which I think it's sort of obvious, but anyway, there's a difference in the data types. So you're trying to write a P to Q, which is from integer to a double pointer, integer pointer to a double pointer. And here it is Q is double pointer, yeah, double pointer to an integer pointer. But R is void. Okay, so this does not complete. Maybe you can think in that direction. What if I write the same thing and put Q? Will that be okay? Let's just, yes, that's also okay. Any guesses? Okay. So the reason is that there's actually the hint, some explanation is the reason. Okay. So the reason is that since R is a void pointer, okay, whatever data type P had or Q had essentially doesn't mean anything for R. Okay. Yes, R is also, what does a pointer have? Actually, if you think about it, pointer has two main portions, okay, ingredients which make it, or as in it completes it. So one is the fact that it stores addresses, okay. It has a certain size, it stores addresses, and the fact that it itself remembers what data type it is pointing to. Okay. Hence we define it with some data type and then say star as to say that is a pointer. Now for P and Q, they have definitely addresses. We are passing them and ampersand I and ampersand D. Okay. But we're also defining what is the data types. So this is integer, this is double. For a void, it knows that it is essentially a null data type, as in there is no data type for it. Okay. So when you are passing P, like rewriting R equals to P and R equals to Q, okay, what essentially happens is you are copying the addresses from P to R and again from Q to R, okay, in both the cases. But anyway, R doesn't have a data type. So whatever data type you are trying to pass from on the right hand side, it doesn't matter anyway. Okay. So that is the reason for only void pointers, you can do an implicit cast. Okay. So this is implicit casting from what was the integer pointer to, sorry, void pointer. Okay. And here it is implicit casting from double pointer to void pointer. Absolutely, you can do the same thing this way also. No problem at all. You can explicitly cast them. Not a problem. Q here. That's absolutely okay. All right. That's it. Yeah, absolutely okay. Just comment these for now. Okay. All right. Any questions so far? All right. What if I do the opposite one? P equals to R. What do you guys think will happen? Will this throw? Okay. It will throw an error. Can you explain why? It's okay. Can get try and attempt. Right. And why is that a problem? It's the opposite. Sorry, my bad. The answer is what you gave is little switched. So it's not from integer pointer to void pointer, it's void pointer to integer pointer. Okay. So the reason is that when you're trying to convert a void pointer to a integer pointer, okay, um, this is something which is by the standard, it doesn't allow you to do it implicitly. Okay, because the same address, if you want it to be treated as a integer, okay, because now you imagine you had a pointer which pointed to nothing. Okay, it's like basically there's no data type. It was pointing, basically it has an address and it is pointing to some address, and that from that address there'll be few there'll be some bits. Okay, we'll be reading or not reading or whatever. The point is, the take home message here is that when that address is being pointed to and it doesn't know what that address is, doing an implicit casting by the compiler is not allowed. The main reason for that is it can obviously uh, lead to a lot of issues and errors. Okay, so implicit casting is not allowed. Again, the natural question then comes is, uh, casting from, let's say, some here, let me just write it, it's okay. From void pointer to integer pointer. Actually, here you can be, I'm sure you can uh, get convince yourself that if it was a double pointer also, it would have failed. Okay? So maybe we'll just put that also. Okay, all right. Let's run it and see. Yeah, exactly. So the both of them actually fail. Okay, you cannot convert integer pointer or to integer pointer or double pointer from a void pointer. Okay, but then again the natural question comes, but is that not something sometimes we want to do? As in, we can pass around pointers which are void type and treat them separately to another data type. So maybe I'll treat it as a double in a certain instance and the same pointer as an integer in another instance. And to pass it around, okay, to functions and classes and such, I can have them as void pointers because again, I don't have to worry about its data type. But for the certain case itself, just inside the function body, okay, depending on wherever it is, I can just convert its data type to one or the other. I should be like something like that actually. Sorry, this is double. Yeah. So something like that is actually does seem one should be able to do, right? As in, there is a use case to that. That's exactly why C++ allows you to do this conversion, but explicitly. So you have to convert it, your void pointer, explicitly to, yeah, exactly. Oh, absolutely. That's a very good example. So when you do malloc, right, you are converting. So essentially, that's a void pointer. When you're trying to do malloc, it gives you a pointer. We try to typecast it to our required data type. All right, that's exactly true. It's a very good example. So in that case, you ask for certain bits. So, yeah. So there are some, how to put it? Uh, yeah, the way to look at this is you had uh, through malloc, okay, you ask for certain bits or bytes of data, and that chunk of memory can be used to store any inbuilt data type, integer or float, right? So when it returns a pointer, it's actually a void pointer, okay, because ideally you can use it to store anything. We explicitly typecast it to integer pointer or double pointer or float pointer or whatever when setting it to whatever pointer we want. Okay. So as in if we decide to store the return of the malloc pointer as a float, then we'll define integer pointer float, let's say f, okay, sorry, float pointer f, okay, equals to the typecasted float pointer on the malloc. Okay. Guys must may have seen the malloc command before in C++, sorry, in C. Okay, it can be used in C also, but more of a thing from C. Okay. Same thing you can do as through new also, new and delete operators. So the new operator also returns a pointer. pretty much you can typecast that also and then store it in whatever data type you want. Okay. So to explicitly say that I want my R to be converted to an integer pointer, okay, and then store it, let my P store it after converting it to integer pointer. This again is explicit conversion and is actually allowed. Okay, it's very useful to in certain cases, especially again. Remember, this has sources of like this can lead to errors and all, but as in bugs, I would say. But if you know what you are trying to do with the same pointer and through seeing in different portions and directions, okay, you have to what do I put it? Uh, you just have to be careful. Okay, you can. It's a very powerful tool. You have the same pointer. You're just passing around and converting to different data types, and then treating it as a different number. Okay, it does give you that powerful feature, but one has to be very careful while handling that. Okay, so this is explicit. Sorry, casting from void pointer to integer pointer. Okay, let's run this and see. These two will throw errors, so let's just comment them. Yeah, not a problem. So after the explicit casting, this is absolutely okay. All right. Same thing we can do for Q. All right, let's compare that. Yeah, absolutely fine. Doesn't throw any errors. All right. So I hope this you guys get the uh, main idea here. Okay. Any questions? Okay. Another thing, if you guys remember, I had the defined another um, array. Okay, a C-style array containing 10 values, and A was the data type. Okay, the variable name. These are all integers. Okay, so now let's use that also. So what we'll now do is set P as A. Okay, remember A, the variable, when we define it this in this syntax, the C-style array, we are saying we want 10 integers. Okay, this comes from the data type. So 10 is the number of numbers that of whatever data type we have. Okay, so there will be 10 of these of what? Now it is integers. Okay, the variable A itself is actually a pointer. Okay, to the starting address of this array. Okay, so starting address A is known. So remember we used to make for loops and use bracket operation and then put, let's say, ith element as A of I. Okay, remember I told you about dereferencing. So accessing ith element is essentially doing a pointer arithmetic. You do A plus I. Okay, maybe I'll just repeat, like just show that again here. So let's define 10. Okay, so I starts from 0, I less than 10, I plus plus. We access A of I, okay, and set it to just I. We'll do it 10 times. Okay, run it. Yeah, not a problem. Okay, absolutely fine, works. Then another loop, which essentially just prints it. We print the ith value. Okay, as AFI, and then just end the line. Just to say that we actually wrote the values, so it prints from 0 to 9. Fine. Okay, good. The other thing is that the same AFI, okay, can also be thought of in this way. So A, we move by I, okay, and then dereference it. So very similar to that, we can do it in this way also. All right. Yeah. So what we're trying to do is maybe I'll just yeah. So what I'm trying to essentially say here is the AFI or the bracket operator is actually a dereference operator. It essentially does this itself. It actually returns this. It just so happens that it is hidden under this function, which is the bracket. Okay. So for the ith position, we shift the starting pointer by I, but how does it know how much bytes it has to move? That it knows from A, the data type of A. Okay. All right. And then dereferencing it accesses the value there at that position. Okay. That's sort of the idea. Okay, so I hope this is clear. The A is essentially the variable. Okay, it is also a pointer, like here. Okay, like it is much similar to P here or Q here. Okay, but maybe a different data type. It's basically like P, but it's a collection of 10 values. All right. So now, if we try to, maybe I'll so show the running this also. It prints exactly the same values. So from 0 to 9. Okay. Whatever this does, exactly the same thing this also does. And similarly here. Okay. What if I set P as A? Okay. What do you guys think will happen? Is it allowed, not allowed? Remember, A is a pointer, okay, of integer type, data type. P is also a pointer of integer data type. They both will store the same exact uh, digits, 64 bits, okay, and both are of the same data type. So the two things that I told you about are satisfied. So will this be okay? Or will it throw an error? Okay, so let's run this and see. Yeah, it's absolutely okay. This doesn't throw an error because now P is just pointing to the same address location of A. It's absolutely allowed. Both are integers, integer pointers. Both have the same um, size. Okay, everything is good. But what if you try to do the opposite? Okay, this time I'll give you guys the answer. That will throw an error. Reason being, A is a collection of data and they have allocated memory for it. Resetting A to some other address is not allowed. Basically, then what you're doing is, let's say A was pointing to some address called, let's say 100. Okay. Now you're saying, I'll set A to P. Let's say P points to address 50, let's say. Now I'll set A to 50, B 50. But it may so happen that 50 from 50 till the next 10 values, let's say 40 bytes, 40 because 10 and then integer is 4 bytes each. So that from 50 till the next 40 bytes, I actually might not have access in my program. Okay, so you can actually, I mean, you can actually run into some really bizarre issues. Okay, if that is allowed to be done. So that is one. Second thing is what happens to the address of whatever this A was pointing to, 100 itself. So A was storing the value 100, the address, okay, and it ensured that the next 10 values are accessible to the program. When you override that, what happens to that data? How does one even release that data or something, right? So you have dangling pointers. Basically, it's like um, allocated memory, but not freed. You did not reallocate that memory. It's just there. Okay. So because it can lead to such issues, this statement, okay, this is not allowed. You cannot store, even if they're the same data type. So it definitely satisfies the two conditions that I talked to you guys about. Okay. One is the one thing is that both of them are integer pointer data type, and both of them have the same sizes, but because A is a array, okay, this overwriting of the array is not allowed. Okay. All right. Any questions? So the basically for two main reasons. One is that when you overwrite A, you lose the address it was pointing to, and then there's essentially no way to know which address it was pointing to, and you won't be able to deallocate that memory. Okay, maybe this is this. Okay, okay. All right, so that's one. The second thing is after you assign the address, right, to whatever the earlier as a P was pointing to 50, and let's say now A points to 50. The next contiguous values, in our case, it will be 10 of those. Okay, that might not be possible to access. Okay, as in it's possible that it doesn't belong to your program. Maybe it belongs to some other program, but it was not allocated for you. Maybe that can happen, and so you'll be accessing data from another region which is not you're not supposed to. Okay, so to avoid situations like that, this line is not allowed. Okay. Right. Okay. That case, you guys have any questions? Okay. No questions. I think we've covered that much today. Um, yeah. There are more extensions to this typecasting, which we'll look at in the next class. So things do get a little more involved when you have not just inbuilt data type pointers, but let's say the user defined data user-defined pointers, like data types. So like the classes. So classes are like user-defined data type, right? So when you have pointers of those kinds, how does this casting and recasting happen? And yeah, things like that. We also see the same thing as how do we do casting in the C++ way? Um, there, there are different ways of casting, okay, like type casting. This so happens that all of them mean the same thing in C, but because to make the intention of the developer more clear, okay, or basically the line of code or the syntax to be more explicit and clear, we have different versions of typecasting in C++. Okay, so we'll look at that also. All right. Um, right. If you guys have any questions, you can ask. Else, feel free to leave. I'll be here if you have guys have any questions. Okay. And yeah, again, do practice. And again, that's something same thing I'll always repeat. Do practice. The more you write these codes, the better you understand. Okay. And yeah, happy coding. All right. I'll see you guys next week. And as we discussed, we'll see more of the typecasting forms for classes and other user-defined data types. Yeah. Okay.